Hi guys, so in this lesson we're going to evaluate some special limits that we're going to use throughout the rest of this year. So just to get us started, let's start by looking at this limit here of x minus 36 over the square root of x minus 6. And we want to know what happens as x gets closer to 36. So if we just plug that value in, you'll notice that we get 0 over 0, which is an indeterminate form. So we've got to do something else. So I'm going to have you pause right now and see if you remember how to evaluate limits like this algebraically. So what you should have done is multiply by the conjugate, because I have that square root there. I have the square root of x minus 6. We're going to multiply by the square root of x plus 6 over the square root of x plus 6, because this expression here really is just the number 1. Which is why I'm legally allowed to do that. So finding the product now of the denominator. Why did we pick the conjugates? Well, to make the denominator nice, it's the difference of squares, so it's x minus 36. And I'm just going to leave the top alone. And beautifully, we can divide out that common factor to 1, and we're left with the limit as x approaches 36 of the square root of x plus 6, which now we can actually take the limit of as x gets closer to 36. This gets closer to 6, plus 6 is 12. So again, when we encounter these indeterminate form limits, we have to realize what algebraic strategies do we have. And if we see square roots, using the conjugate is definitely an option. So the first special limit I'm going to have us explore today is this function of sine of x over x. And I want to know what's happening around 0. What's the limit as x approaches 0 of sine of x over x? So the first thing we need to do is realize what numbers are in the neighborhood around 0. Just quickly reviewing here. Got like 0.1, 0.01, 0.001. Those values are approaching 0 from above, from the right. Then people always use 0.99s here, but that's close to 1. We want to use 0.001, negative 0.01, negative 0.1. Those are the values close to 0. And if I want to evaluate this limit, my first try should be just plugging in 0. What's the sine of 0 over 0? Well, sine is the height on the unit circle, so at 0 degrees it has a height of 0. We get another indeterminate form there. So I'm going to have you guys pause, take out your calculators, and take a second and try to create your own table here to see if you can actually evaluate the limit as x approaches 0 of sine of x over x. So switching over to Desmos here, you'll see that I have my table made here. Clearly these values, as I get closer to 0, get closer to 1. And graphically, we'll see that too. Luckily, I can just pinch and squeeze my graph to make it look nice here. As we get closer to 0, this function gets closer and closer to 1, but there is that hole at x equals 0 with a height of 1. So what we can conclude is the limit as x approaches 0 of sine of x over x is actually 1. And this is a special limit that we're going to have to use over and over and over again throughout this course. So just make sure you realize that when we have sine of x over x, it does equal 1. And you can take a second and sketch a graph below. The key thing here is it has this kind of shape where it has a hole at 1, and then it comes back down. At 0, there's a y value of 1, but there's a hole in the graph, because 0 over 0 is not defined. So what we're going to do is we're going to start encountering limits that look like sine of x over x. And we're going to use that value, we're going to use that limit to evaluate limits that look like it. Oh, come on, Sparky. There we go. All right, so here I have the limit as x approaches 0 of sine of 2x over 2x. And at first you might be thinking, well, this is completely different, but if I take a second and I say as chicken nugget gets closer to 0 of sine of chicken nugget over chicken nugget, that's the exact same limit I wrote before. Just instead of using an x, I used a chicken nugget. right? We know that limit equals 1. The limit as x approaches 0 of sine of x over x is 1. So if I just change that x into a chicken nugget, the sine of something over that same thing, that should equal 1. So here, if I take the limit as x approaches 0 of sine of 2x over 2x, it's the sine of something over that same thing. This limit equals 1. Again, I could have made that any number I wanted. I could have made that the sine of 10x over 10x. That equals 1. What's up, Ms. Pressler? So this next one looks like the limit of sine of x over x, but there's a 7x inside there, which means ideally I would want to make this the limit of 7x over 7x, because I know that would be 1, but I don't have 7x there. And it would be illegal for me to just put a 7 in the denominator of this expression. That would change its value. So what we need to do is get creative and say, well, if I put a 7 in the denominator, and you all should have just said put a 7 in the numerator. So at this point, I have 7 times the sine of 7x over 7x. So the answer is 7. Because this whole expression, the limit as x approaches 0 gets closer to 1. 1 times 7 is 7. And finally over here, again, it looks like a sine of x over x problem, but there's that 3 in the way. And I can't just put a 3 inside a trig function. That would be crazy. We're not even going to think about that. But what we can do is notice the structure of this expression and say, wait a minute, it's really, I already have the sine of x over x. There's just a 1/3 there, right? 1 over 3. Well, this expression gets closer to 1, 1 times a third. This ends up being 1/3 is the limit. So using that value of sine of x over x, we can solve other limit problems that look similar to it by recognizing the structure, or by saying I need a 7, let me multiply the numerator and denominator by 7. So here's a lovely trig function. H of x is cos of 5x over 8x cotan of 2x. I want to know the limit as limit of h as x approaches 0. So I see cotangent, and I immediately am thinking, well, cotangent, I can rewrite that as the cosine of 2x over the sine of 2x. Right? Cotangent is the reciprocal of tangent, sine over cosine, so this is cosine of 2x over the sine of 2x. And that 8x is just hanging out there in the numerator. And then I have a fraction, a fraction in the denominator here, so I'm just going to multiply by its reciprocal. And now I'm here. And I need to take the limit of this at some point. And I think I'm just going to kind of rearrange some people now, because I see sine of 2x, these cosines don't bother me, and I have an 8x on the bottom there. So I really want to take the limit as x approaches 0 of the cos of 5x, sine of 2x over the cos of 2x, and well, I have the sine of 2x, so I really want a 2x here. And I'm just going to literally use second grade right now and say 8x. Instead of writing 8, I wrote 4 times 2. So now I've created that sine of 2x over 2x there. I've created that expression. That expression gets closer to 1. The limit as cosine gets closer to 0, well, that gets closer to 0, and the cosine of 0 is 1, right? The height, the horizontal displacement, the horizontal distance of the unit circle at 0 degrees is 1. So we end up with 1 over 1 times that whole limit is 1, and there's a 4 in the denominator. So in the end, the limit as x approaches 0 of h of x is 1/4. And we didn't even do calculus until this last step here. All of this was just algebraic manipulations and realizing 8x is really 4 times 2x, because I needed a 2x to match that chicken nugget inside the sine of x. So at this point, for these next 3 questions. I just want you to explore the limits using the table and graph. There's nothing really crazy to do here. They are some limits I'm going to point back to at some point in future lessons, but just use a table and a graph to see if you can evaluate the next 2 limits. The last one is a disaster, so you can just play around with that on Desmos. But 4 and 5 are important limits. They have actual values. The last one is a mess.